So here's just a quick review on the elastic behavior for materials. We introduced the concept of Young's modulus, bulk modulus, and shear modulus. So these are grouped together and described as being the elastic moduli for a material. And it all has to do with ratios of stress to strain. And in particular, if we focus our study of stress to strain to materials that are only stressed up to their proportional limit, then we can say that the ratio of stress to strain is a constant value. So whether that stress comes in the form of tension, like tuning a guitar string, or compression, like overloading a femur bone, in some cases stress is the additional fluid pressure acting on an object, or stress can even be the shear forces that are applied by a pair of scissors. In any case, there's some numerical value that describes the slope of this graph, and that numerical value is the elastic modulus. So in the case of tension and compression, the elastic modulus is known as Young's modulus. In the case of fluid pressure, the ratio of stress to strain is referred to as the material's bulk modulus. And in the case of shears, well, there's no clever name for it, it's just called shear modulus. In every case, there's a formula that gives you the value of Y, Young's modulus, or the value of B, bulk modulus, or the value of S, shear modulus. But make no mistake, all those values are nothing more than the slope of this graph within the proportional limit of stress to strain. So as a quick review, for the case of Young's modulus, either tension or compression, that constant of proportionality is just a ratio of stress over strain, where stress is given not just as force, but force per unit area, and strain isn't just the change in length, it's the percentage change in length. Likewise, we have an elastic modulus known as the bulk modulus, and it's also a ratio of stress over strain. Here, the stress is measured as the additional fluid pressure, and the strain is measured as the percentage change in volume. Lastly, shear modulus, the stress to strain ratio, once again, is units of force per area over a fractional change in displacement. So notice the units in every case. For Young's modulus, the numerator is in units of newtons per meter, and the denominator has no units because it's just a percentage change. Well, a newton per meter is the same thing. This is area, newton per square meter. A newton per square meter is known as a Pascal, and often Young's modulus is expressed in units of gigapascals. Same thing for bulk modulus. Pressure is measured in pascals, and you can see the denominator has no units. So the bulk modulus of a material is also measured in pascals, or more commonly, gigapascals. And the same is true for shear modulus. Force per unit area is newtons per square meter. X divided by h is also a dimensionless quantity. And newtons per square meter are pascals. And if the shear modulus is large enough, it would be expressed in some amount of gigapascal.